What is regression? Regression is a statistical way to establish a relationship between a dependent variable and a set of independent variables. For example, if we say age of a person is 5 plus height into 10 plus weight into 15. Here we are establishing a relationship between height and weight of a person with his or her age. This is a very basic example of regression. So given a set of independent variables, we have to determine the value of a dependent variable at any point of time. So that will be regression. Now we come to linear regression. What is linear regression? It is a supervised learning algorithm that learns from a set of training sample data. It estimates relationship between a dependent variable, which is also known as target or label, and one or more independent variables, which are also called predictors. Assumptions of linear regression are: not a single size fits for all in regression. The same is true for linear regression as well. In order to fit a linear regression line, data should satisfy a few basic but important assumptions. So assumptions have to be made that the model will fit the data on, or the training data on. If your data doesn't follow the assumptions, your results may be wrong as well as misleading. So what are these? Linearity and relative normality of error distribution, homoscedasticity, and statistical independence of errors. These are the assumptions that we mostly use. Objectives of linear regression: establish if there is a relationship between two variables. For example, relationship between housing process and area of house, number of hours of study and the marks obtained, income and spending, and so on. Prediction of new possible values. Based on the area of house, predicting the house prices in a particular month. Based on the number of hours studied, predicting the possible marks, sales in the next 3 months, and so on. So these are the use cases of linear regression, where we predict the value of the dependent variable given a set of independent variables after we have already trained the data on existing independent variables data along with the target for those. Now we see the linear regression use cases in detail and their examples. First one example is real estate. For example, to model residential home prices as a function of the home's living area, bathroom, number of bedrooms, lot size, etc., we can classify the or we can get the home price, which is a function of all these criteria. Second example would be medicine. For example, to analyze the effect of a proposed radiation treatment on reducing tumor sizes based on patient attributes such as age or weight. So given past data about age and weight of patients and how they survived the radiation treatment, we can predict the effect of a radiation treatment on current patient given his age or weight. So third example would be demand forecasting. Example, to predict demand of goods and services. For example, restaurant chains can predict the quantity of food depending on the weather. So this is a nice example of linear regression. Marketing. Example, predicting company sales based on previous month's sales and stock prices of a company. So even we can predict company sales given its conditions. Types of linear regression. First one is univariate linear regression, where there is only a linear dependency on the dependent variable on the independent variables. So dependent variable here is y and independent variable is x1, and there is a linear dependency on x1 of y. So this is univariate linear regression, where there is only one variable, one independent variable. So this is thus univariate. Then comes multivariate linear regression, where there is a linear dependency on a number of independent variables x1 to xn, and y is a dependent variable. Next one is a polynomial linear regression, in which there is a polynomial dependency on multiple independent variables x1 to xn. So everyone has their powers here, separate powers. It can be a polynomial as well. Now we discuss univariate linear regression. In univariate linear regression, the regression line gets fit more during the training period. This is a sample data in which we have the blue points as the training sets data, and the red points as the test set data. And this is our predicted line, linear regression line. In simple linear regression, you predict scores on one variable from the scores on a second variable. So given a set of scores of one variable, we predict the set of scores for another variable. The variable you are predicting is called the criterion variable and is referred to as y, or the target. The variable on which you are basing your predictions is called the predictor variable and is referred to as x. When there is only one predictor variable, the prediction method is called as simple regression. So this is also a case of univariate linear regression, or simple. It is also termed as simple linear regression. The predictions of y when plotted as a function of x form a straight line in simple linear regression. Case study of housing prices prediction. So given a area of a house, we have to predict its price given a few set of data of area and price. In the following example, consider you have a data set consisting of the individual area of several houses and their respective prices. You wish to build a predictive model using this data set that can predict the price of the house based on the area fed to it. So on the x-axis you have the area in 1000 square feet, and on y-axis you have the price. So basically we have to predict, given an area, what will be its price. If we plot the given data in the following format, considering x-axis as the area of the house and y-axis as the price of the house, we get the following points marked in cross here, this and so on. In this case, x-axis represents the independent variable, predictor variable, or regressors. Y-axis depicts the dependent variable, criterion variable, or regressant, which is the price of the house. In this case of housing prices prediction, consider two known people. Your friend who is new to the real estate business and has just started the business, completing two deals so far. So he is a newbie in this business. Or consider your colleague who is into the real estate business from last 25 years. So your colleague would have consumed more data about the flats during his 25 years. Now in this example, you need to buy a property in the city. Your colleague can prove to be more correct in suggesting the price compared to your friend, and the reason is data. So your colleague has consumed more data compared to your friend, which makes him more correct. Similarly, in machine learning, the more you feed data to the algorithm, the better and effective algorithm you can build. Let us consider a straight line as a predictive model. We start from considering first 2 points. So given first 2 points, we mark a straight line from them. Let us calculate the error for current straight line x is equal to 3200 square feet. I mean for x is equal to 3200 square feet point, which is this one. Let us calculate the error for, if we take the linear regression line as this line here. So error is y minus y cap. So actual value is this, predicted value is this. So that will be our error. Now consider that you draw another line that is green as shown below. So this will reduce the error as the new y cap here is more near to the actual y. So this reduces error and fits more points. In the following image, where we fit the line to cover more points, you can see in one of the cases for 7th sample, which is at 6000 square feet, value of x approximately, the error is positive, whereas for 8th sample, which is at 7000 square feet, value of x approximately, the error e is negative. So you can see here the error y minus y cap is positive, and here it is negative. Now we discuss the cost function. J is equal to 1 by 2n summation I is equal to 1 to n into yi minus yi cap whole square, where yi is the output actual at the ith input, and yi cap is the predicted output at ith input. Final cost function can be depicted as j of mi of c is equal to 1 by 2n summation I is equal to 1 to n yi minus yi cap whole square, where n is the number of observations in the data, yi is the actual value, and yi cap is the predicted value. Here, the cost function for linear regression is convex in nature. One of the most important property of convex function is that it is guaranteed to provide the lowest value when differentiated at 0. So the cost function is convex in nature, and we can get the minima of that. Now you can describe the final understanding of a prediction of a continuous parameter in the following manner. The regression equation is y cap is equal to mi xi plus c, where parameters are mi and c, which are the slope and the constant. Cost function j mic, cost, this is cost function as a function of mi and c is 1 by 2n summation I is equal to 1 to n yi minus yi cap whole square, and the goal is to minimize the cost function. Now the goal is to minimize the cost function by updating the parameters m and c. Let's take the partial differentiation of cost function with respect to m and c. So we will get this dou j by dou m is equal to 1 by n summation I is equal to 1 to n yi cap minus yi xi. So from the definition of yi cap is equal to m into xi plus c, we get this definition of dou j by dou m, partial derivative of error cost, the cost function with respect to m. Gradient descent. To compute m and c more effectively, gradient descent comes into the picture. For a particular value of m and c, gradient descent works like this. First, it calculates the partial derivative of the cost function. If the derivative is positive, it decreases the parameter value. If the derivative is negative, it increases the parameter value. The motive is to reach the lowest point or 0 in the convex curve where the derivative is minimum. So the cost function will be minimum there where the derivative is minimum. So it progressive iteratively using a step size eta, also called as learning rate, that is defined by the user, but make sure that the step is not too large or too small. Too small a step size will take longer to converge, and too large a step size will never reach an optimum. Hope this is clear. So we discussed the gradient descent algorithm for linear regression. Repeat until converge. Wj is Wj minus learning rate into partial derivative of j with respect to Wj, where W is the parameter can be coefficient and constant, which are m and c. So we have to update both with this equation respectively, and simultaneously update at j is equal to 0, j is equal to 1, and so on. Now we discuss the consequences of the learning rate value. Learning rate can be written as LR. If LR is too small, gradient descent can be slow in converging. So if we have a small step size here, in this case, and this is the curve that represents the cost function, which has minima here. This is again the minima is here. So if you have a small step size, this will come from here to here, the error then will come from here to here, then so on. It will move very slowly up to here. So it will take a lot of time in converging to the minima. If LR is very big, gradient descent can overshoot the minimum. So this is the large step size case. So if the running rate is very high, the change will be drastic in the cost function, and it may even skip the minima. So suppose it is coming from here to here, from here to here, so from here to here, so it might Next, come from here to here again and move from here to here. So basically it will skip the minima as shown here. So the following overall process is called linear regression to build a linear predictive model. So basically we should choose a particular learning rate in our linear regression model so as that we either it is not either large nor too small. Gradient descent algorithm and linear regression model. So on the right side we see the equation for prediction and the cost function, and on the left side we see the gradient descent algorithm for that. Regression model performance. After you build the model, the next logical question comes in mind is to know whether your model is good enough to predict in future, or the relationship that you build between dependent and independent variables is good enough or not. So you want to test whether your model is efficient enough. For this there are several metrics. Metrics mean performance criteria. First one is the R square metric. Second one is the root mean square error metric. Third one is the mean absolute percentage error metric. Regression model performance metrics R square. So R square is given as TSS minus RSS by TSS, where RSS is the predicted value and TSS is the total sample value. Next one is the root mean square error or RMSE. It tells the measure of dispersion of predictive values from the actual values. So it is a measure of dispersion of the values that the model predicted from the actual values. It is a statistical term dispersion. The formula for calculating RMSE is R square is equal to 1 by n summation xi minus mean x into yi minus mean y divided by dou x into dou y whole square, where n is the total number of observations. Finally, we move on to mean absolute percentage error or MAPE. To overcome the limitations of RMSE, analysts prefer MAPE over RMSE that gives error in times of percentages and hence comparable across models. Formula for calculating MAPE is m is equal to 1 by n summation t is equal to 1 to n modulo of at minus ft by at. Improving the accuracy of a regression model. There is little you can do when your data violates regression assumptions. An obvious solution is to use tree-based algorithms that capture non-linearity quite well. But if you still want using regression, following are some tips you can implement. It may be possible that all the features may not have good correct correlation with the label. In that case, your data is suffering from non-linearity. You should transform the independent variables using sqrt, log square, and so on. So this is dimensionality reduction, and we should do this using sqrt, log square, and so on. Sometimes it may be possible that your data is suffering from heteroscedasticity. Transform the dependent variable using sqrt, log square, and so on. So heteroscedasticity can be avoided by using the sqrt log n square functions. In such scenario, you can also give a try using weighted least square method to tackle this problem. So it can also be used in case if the data is suffering from multi-collinearity. Use a correlation matrix to check correlated variables. Let us say variables A and B are highly correlated. Now instead of removing one of them, use this approach. Find the average correlation of A and B with the rest of the variables. Whichever variable has a higher average in comparison with other variables can be removed. So the more the correlation, the more it is not related to the data set. Alternatively, you can use penalized regression methods such as lasso, ridge, elastic net, and so on. You can perform variable selection based on p-values. If a variable shows p-value greater than 0.5, you can remove that variable. Since at p greater than 0.05, you will always fail to reject null hypothesis. Multiple linear regression. If you have more than one independent variable, the procedure for fitting a baseline is known as multiple linear regression. Fundamentally, there is no difference between simple and multiple linear regression. Both work on OLS principle and procedure to get the best line is also similar. In the latter case, regression equation will take a shape like this: y is equal to m1 x1 plus m2 x2 plus m3 x3 plus so on up to mn xn plus c. Here, according to the number of independent variable, the number of parameters will increase by n plus 1. If there are n independent variables, the geometry you can assume is a n-dimensional hyperplane. Feature engineering for multivariate linear regression. We can do one-hot encoding for when some inputs are categories rather than numbers. For example, age. We can represent the category values as numbers so that they can be used in our linear regression equations. So in this case, we have created dummy variables on the right, which are New York and California, and they have either 1 or 0 to say that the state is New York or California. So this is known as one-hot encoding. In this slide, we see feature scaling. First one is mean normalization or standardization, and second one is min-max normalization or normalization. So this uses the standard deviation, and this uses the min-max normalization. In this slide, we briefly discuss cross-validation. So given a set of data, this is the full data set. To build our model, we split it into training and test data set so that the model is trained on the training data set, which is given in pink here, and finally it is tested on the test set out of the same data set, which is in black here, and so on. Fold 3, fold 2 here, and fold 1 here. This is test set. So there are 5 splits in this scenario. Multi-fold split is being discussed. So there are 5 splits of this data set in which there are 5 folds each in each split. Fold means a set of data from that split. So in this case, the first one is taken as a training set. In this case, the second fold is taken as a, not the training set, the test set, sorry. This is the first set is taken as a test set, the second is taken as a test set here from the split 2, and so on. This is multi-fold cross validation. So as discussed, pink areas are folds of data that are included in training set and black ones are test sets. 5 folds is 5-fold cross validations or CV. 10 folds is 10-fold CV. K folds is K-fold CV. More folds implies more computationally expensive. So the more the folds, the more the time and resources the computer takes to generate the model. Now we discuss overfitting and generalization. As you train your model with more and more data, it may start to fit the training data more and more accurately, but becomes worse at handling test data that you feed it to later. This is known as overfitting and results in an increased generalization error. So what is overfitting? When the model is adapting more to the training set but not giving the right or giving more errors when test data is input to it. So this is known as overfitting and results in an increased generalization error. Large coefficients lead to overfitting. So as discussed, we should use learning rate appropriately, and large learning rate can lead to overfitting. Penalizing large coefficients implies regularization, which we will discuss in coming slides. First one of penalizing regularization is L1 regularization or LASSO, least absolute shrinkage and selection operator. Having a large number of samples with respect to the number of dimensionality D increases the quality of your model. One way to reduce the effective number of dimensions is to use those that most contribute to the signal and ignore those that mostly act as noise. So if we are given a number of samples or features n, sorry, number of samples n with respect to the number of dimensionality d. We are given d-dimensional features. Then how we reduce the dimension is dimensionality reduction, which we will discuss in coming slides. And after reducing the dimensions, we select those that don't act as noise mostly, and others we drop those that mostly act as noise. L1 regularization achieves this by adding a penalty that results in the weight for the dimensions that act as noise becoming 0. So for those dimensions that act as noise, it equates them to 0. This is a penalty given by L1 regularization for algorithm, and L1 regularization encourages a sparse vector of weights in which few are non-zero and many are 0. Depending on the regularization strength, certain weights can become 0. That makes lasso a supervised feature selection technique. So this is the formula for cost function in case of L1 regularization. A lambda, specific lambda is chosen, which is multiplied by the mod of weight at that dimension. A limitation of lasso is that it selects at most n variables if m greater than n. And now we discuss another type of regularization, which is ridge regularization or L2 regularization. Another way to reduce the complexity of the model and preventing overfitting to outliers is L2 regression, which is also known as ridge regression. Now, what is meant by this? Suppose we have formed a linear regression line, and outliers in this case will be those set of points which are lying outside that line. So, overfitting, what will it do is it will fit the line to those outliers as well, but which is sometimes not required and gives us generalization error. So basically, we have to the L2 regression. What it does is it penalizes those outliers by introducing an additional term to the cost function that has the effect of penalizing large weights and thereby minimizing this skew. So ridge regression is an L2 penalized model where we simply add the squared sum of the weights to the least squares cost function. So this is lambda is the hyperparameter here, and instead of wi we use wi whole square. By increasing the value of the hyperparameter lambda, we can increase the regularization strength and shrink the weights of our model. The more the lambda, the more compact our model is. Finally, we can use L1 and L2 regularization both together, which is also known as elastic net algorithm. L1 regularization minimizes the impact of dimensions that have low weights and are thus largely noise. L2 regularization minimizes the impacts of outliers in your training data, so both perform their individual functions. L1 and L2 regularization can be used together, and the combination is referred to as elastic net regularization. As the differential of the error function contains a sigmoid that has a no inverse, you cannot solve for W and must use gradient descent. So in this elastic net scenario, we must use gradient descent as the differential of the error function will have a sigmoid that has no inverse. So we cannot solve for W. Now we move on to multi-collinearity. Multi-collinearity tells us the strength of relationship between independent variables. If there is multi-collinearity in our data, the beta coefficients may be misleading. Next is VIF or variance inflation factor, which is used to identify the multi-collinearity. If VIF value is greater than 4, we exclude that variable from our model building exercise. Multi-collinearity is basically the intercollinearity between independent variables, and for if a specific for a specific feature, if the VIF value is greater than 4, we exclude that feature or variable from our model building exercise. VIF is variance inflation factor, and it is used to identify that multicollinearity. Finally, we discuss iterative models. Model building is not a one-step process. We need to run multiple iterations in order to reach a final model. One needs to take care of p-value and VIF for variable selection and r-square and MAP for model selection. So basically we need to take our parameters and tune them iteratively so that we can reach a final model And because model building is not a one-step process, we need to run multiple iterations in order to reach our final model.